Hi everyone, Mr. Roloff here, and today we're going to be talking a little bit about solubility, and that's going to be a little bit of a continuation of the first notes that we took labeled the solutions vocabulary, the guided notes. So if you don't have that, make sure you go back and open up that first solutions notes and watch the video. And we're going to continue to build on our vocabulary list, so please make sure you have that handy, because remember, that is a tool you can use on the test. So where we left off with those solution vocabulary notes is you should have done a mini lab that basically you were finding this right here is really the golden goose, I guess you might say, for polarity, is that like dissolves like. And hopefully you found that after the lab that our polar solutes were dissolving in polar solvents. So polar dissolves polar, nonpolar dissolves nonpolar, and of course if we try to mix polar with nonpolar, it doesn't mix very well. So that's hopefully what you found from the lab. Today we're going to dive into a few applications of where that is actually relevant to us in real life. So just a quick pause here, and if I go too fast for you to fill in the notes, feel free to hit the pause button and go back and add these. But these are two words that you should have. I think you should have immiscible. Remember, that means two fluids that don't mix with one another. A really good example of that would be something like oil and water. Oil and vinegar is another good example where they don't mix and they form, remember, two layers. All right, so we get two layers out of this. You can actually pick out, the polar and the nonpolar. However, here's one that you probably do need to add: miscible. All right, miscible, it's the opposite of immiscible. It means that they do mix together. So an example of this might be something like ethanol and water, both two polar substances that will mix together. And some more examples. So we said oil and water. Would that be miscible or immiscible? Well, you can almost picture the oil kind of layering on top of the water, so that would be immiscible. What about our water and rubbing alcohol? So water, we should know at this point, is a polar molecule. And alcohol, you could probably see that OH there. That tells us that's also a polar molecule. Like dissolves like. We can't say that enough. Like dissolves like here. That tells us that you can actually see in the picture even that it is miscible, that it has kind of mixed together, if you will. And the same thing applies for nonpolar and nonpolar. Here's an example of tetrachloroethylene. This is actually the main ingredient for dry cleaners. So how do they, quote unquote, dry clean without water your fancy clothes? Well, right here, tetrachloroethylene is just carbon and chlorine, and it is a nonpolar molecule. So if I were to mix that with something else that's nonpolar, like oil, we would also see those mix, because likes dissolves likes. So an example of how like dissolves like, and even in our body here, vitamin C. Where do we get vitamin C from? Well, you probably have heard this before, that you got to drink your orange juice. We most of the times we get it from citrus fruit, and vitamin C helps with things like muscle movement, and there's a lot of OH groups making it really polar for that vitamin C. But the point is that our bodies will utilize the fact that vitamin C is polar, and water grabs onto it. So water is going to dissolve that vitamin C. And we all know how our body gets rid of water. Well, we go take a pee and we get rid of any vitamin C that's still maybe in our body. So, as far as like overdosing on vitamin C, that just doesn't happen, because, our bodies are able to regulate that using our kidneys to get rid of any excess that we might have. Very useful. Now that's different from vitamin A. Vitamin A, you could technically overdose on vitamin A, and that's actually been heard of. It can build up in the body. Why? Because vitamin A is nonpolar. So if it's nonpolar, it's going to dissolve in other nonpolar. So fats and oils, it's going to absorb that vitamin A. And we all know about fats and oils is that our body doesn't have a good way to get rid of that. And so it's really our body's storage method, actually. So, it'll stay in our body for a really, really long time. So next we're going to look at solubility and solubility graphs. This is going to be really helpful for you when you are filling out the homework. The homework is asking you to just basically look at some solubility graphs and tell us a few things about it. So the first thing, here's another definition for you to add to your study sheet there. Solubility is measured as the amount of solute, that's what gets dissolved, that will dissolve in 100 grams of a solvent. And this is at a given temperature and pressure. So really it's measured in grams of our solute per 100 grams of our solvent, and really depends on two things. Number one, the polar nature of the substance, and also the temperature. And we'll see more of that in a little bit. So this is an example of a solubility graph. And the way that you read this is you'll see that here on our y-axis, we have the solubility of our different substances. So let's just focus on KNO3 here for a second. This orange line is telling us that the amount of solubility, so how many grams per 100 grams of water. So imagine I've got 100 grams of water. How much KNO3 can I add to that before it's, say, full? And we've got a word for that we'll hit on in a little bit, but just for layman's terms, we'll just say full. And what do you notice on the x-axis here? And on the x-axis, we have temperature. So our temperature, as we go from left to right, what happens as we're heating this up? As we're heating this up, we see it looks like we can add more of our solute, our KNO3. So as we heat this up, for most substances, you can see LiSO4 is a little bit of an exception to the rule, but for a majority of the time, when we increase the temperature, look what's happening. We can put more of that solute into the water. So here's just a couple of general rules based on what we just saw there regarding temperature. As we increase the temperature, our solvent, the amount of our solute rather, will increase how much we can add to that solvent. If we increase the temperature for gases, it's actually backwards. It's actually the other way around. So we can't put as much gas into our solvent as we can with a solid solute. So we'll hit more on gases here at the end of the presentation, but just so you're aware, it actually flips when we're looking at gases. So this is just a quick link to a video that explains a little bit more in depth about the solubility of solids in liquids. So I highly recommend you check this out. There should be some links towards the bottom of the page after this main video for you to easily find these. If you're looking in the slides themselves, obviously, hopefully these links help you find those. So let's actually look at maybe interpreting how to read some of these solubility graphs. So we already said that we can put more solid into the solvent as the temperature increases. We already said that, and that's, of course, not the case for all. But let's practice this. So I want to focus on this bullet point right here. What is the solubility of NaCl, salt, at 20 degrees Celsius? Well, if I look at NaCl, here's this yellow line, kind of hard to follow, but if I look at that, I got to find my temperature is at 20 degrees. I'm actually going to write that in. So at 20 degrees, if I find where that intersects with my NaCl line, I'm looking at this yellow line, it looks like at that temperature I should be able to fit, 38, 39 grams of that salt into 100 grams of water. And it looks like we went with 35 grams, so 35, 39, 38 would be accurate, okay? So if it's tough to tell on the graph, don't worry, do your best to guess, and we'll take that into consideration when we're actually grading these. So if we hit a temperature of 20 degrees, what that means is that we hit a limit, right? So we max out on how much NaCl we can put into that water. I told you we had a fancy word for that. We call that a saturated solution. Go ahead and add that to your notes. It's another vocab word for us. A saturated solution is a solution that can't take any more solute, so it's full, right? We said that we had a word for full. Here it is, saturated. So what would happen if we actually tried to add even more salt to that water, even though it's already full? Well, what would happen is some of that excess, maybe you've seen this before, if we keep dumping salt, that excess is going to start to collect at the bottom of our container. So we would see some of that salt start to gather at the bottom. If it's not full, here's another vocab word for you to fill in. We call that unsaturated. So this is something that we can actually put even more of our solute in, and it hasn't hit that saturation point. It hasn't hit a saturated solution. It's not full. So if it's unsaturated, it means that we can still add more. So I just want to point this out. What we can do is we can almost mentally think about this. If I look at my KNO3 here, everything underneath this line, we would call that unsaturated. That is unsaturated. We can add more KNO3, saturated, there we go. And anything above that line, now we've reached a saturation point, okay? Anything above this line, this would be saturated. After that point, we're going to see some of that excess start to collect at the bottom. If I go to my salt example, right, if I add more than 35 grams of salt, NaCl, what do I find? Well, that solution is already full. So that any extra salt is just going to collect at the bottom. So in special cases, we can actually create what's called a supersaturated solution. And you'll see this in class. But in case you're not able to see this, we've got a couple of links. They're not long videos, but they're going to show you some examples of some supersaturated solutions. You can do some pretty cool things with them. And some people have actually kind of gone YouTube famous, if you will, for some of their stunts with some supersaturated solutions. So check those out. Basically what happens in a supersaturated solution is we actually force more solute, that's what gets dissolved, into that solvent than it normally would take at a given temperature. So in our previous example at 20 degrees Celsius, maybe we force more salt into that solution, more than 35, by heating it up. And then if we let it cool down nice and slowly, sometimes those solutes will actually stay in the solution. Like I said, this doesn't happen all the time. It's kind of a rare situation, but maybe you've seen some old hand warmers that actually there's like a little disc that you actually click in the middle. Again, you'll see these in class if you're there. Otherwise, you can Google them or check out the videos. But these hand warmers actually solidify and are exothermic, meaning they give off energy, and that's what kind of keeps our hands warm for some of those old school hand warmers. The last thing that we'll talk about is the solubility of gases. We already mentioned that as a liquid heats up, it can hold less gas. Maybe you can kind of picture this like if you have maybe a can of soda or even just a glass of soda. That soda, if it's cold, will actually stay carbonated longer than if it's like a hot summer day out. If I just put that glass of soda out, that carbon dioxide leaves really, really quickly. It doesn't like to stay kind of in the soda itself. So that's a really good example of what you see down here, that as our temperature increases, gases are less soluble. Our warm soda tastes flat. There's no bubbles. Henry's law is basically saying that as we increase the pressure above the surface of the liquid, we can force more gas into it. And if you picture your can of soda, that can of soda is under a high amount of pressure. Soda companies will pack that soda can with as much gas as possible in order to get as that soda as carbonated as possible. So I hope you learned a little bit about solubility, not only with solids going into liquids, but also even gases like we just saw, being forced, I guess, into liquids as well. So if you have any questions, please talk to your instructor and be sure to check out some of those videos. There's some really cool clips in there. Thanks.